That's cool. We're actually 2 minutes early. This is a first with everybody here. And let's give people a couple of minutes to join. So I'll introduce each of you in turn. We have a tight schedule, but I think we'll make it. And but let me introduce you to each other. Perhaps you don't know each other. Michael Spranger, Sony AI. Then Philps, Rothko. Joe Townsend, Fujitsu. Alex Jaimes, Dataminr. And Dragos Margineantu. He is here. We're almost there. There you go.
Yeah.
So you took your private plane to Montana and you parked just outside.
No, that's the experimental plane that we're building. It's autonomous.
Oh, are you going to talk about autonomous taxiing?
What I'm talking is inspired by that. Yeah.
Excellent.
So that's what I've been doing the last 4 years.
Okay, everyone, it's great to kickstart this industry session. As I mentioned, Alex and I talked about this already at AAAI 2020 in New York, and we thought it was going to happen later that year. And we were all going to be meeting in Greece, I think. But then, of course, things changed. But it's great to have it happening despite it being virtual. So we have a program with 10-minute talks and then a discussion. Let me kickstart without delay by introducing Michael Spranger, Chief Operational Officer at Sony AI and Senior Program Manager at Sony Computer Science Labs. Michael is in Tokyo, Japan. He's co-author of Logic Tensor Network papers, including a paper presented here in the workshop yesterday. And I know he's doing some exciting work on cooking recommender systems. That was the example in yesterday's paper, but I don't know if he will actually mention that. So neurosymbolic systems for applications in biomedical and gastronomic discovery. So there you go. Thank you.
Thanks. Thanks, Artur. Of course, I will be very brief in the 10 minutes. It's a little bit more of an overview of the activity that we're doing than anything in particular in a deep way. So I apologize for this. Just to kick us off for a second, if you don't know, Sony AI is a new organization that's been established about a year ago. And our mission is to unleash human imagination and creativity with AI. We are doing a number of projects together with Sony business groups, for instance, in gaming with PlayStation, or together with a company called Sony Semiconductor Solutions, which is producing image sensors. So there's a flagship project we have on imaging and sensing. And then there's one in gastronomy. So I'll say a little bit of what we are doing there in terms of what's public information. And then finally, also, we are driving a lot of the AI ethics discussion in Sony. And obviously, neurosymbolic systems are very important in this area. So why are we interested in neurosymbolic systems? We are working a lot on tasks that require combinations of learning and reasoning. Specifically, we deal with, and gastronomy is really one of the prime examples there. We deal with scattered and incomplete data. There is prior knowledge that is available. It's often wrong or incomplete. So, you want to combine reasoning and learning. And maybe one of the key things for us also is we are very interested in creativity, which I think in many ways is maybe one of the frontiers of AI. And creativity really does require out of distribution generalization, and the hypothesis is that we can only get to systems that are creative if we combine learning and reasoning. The other angle on neurosymbolic systems is we work a lot with domain experts. So that requires, so non-AI experts, right? So domain experts, specifically artists and chefs and scientists. And for them, black box answers are often not enough, and they require interpretability and explainability. And obviously also here, the hypothesis is that neurosymbolic systems can help us address some of those issues. Arthur already mentioned that we did make some fundamental contributions with Arthur and Luciano Serafini also on a new version of logic tensor networks. That is a framework for learning and reasoning, and I'm mentioning this here because this underlies a lot of the work we're doing also internally, which logic tensor networks grounds a first order language in neural networks and fuzzy logic. And we recently released with Arthur and also Luciano this LTN 2.0 that has a number of new features, but primarily actually also shows how LTN can unify many tasks in reasoning and learning. So like classification, regression, and clustering, and statistical relational learning, and things of that nature. So I very much recommend you to see the paper and also look at the code distribution that we now have, which I think is very nice in terms of examples. We then use these systems, and this is a paper in NeSy 2 years back. I guess it's 1 year back, if you just count the number of occurrences of NeSy, where we worked on applying logic tensor networks or neurosymbolic systems to reinforcement learning. And the primary point of this work was actually to show that if we encode prior knowledge in logical rules and give this in a specific way to reinforcement learning agents, then we're able to have these agents generalize across different scenarios or different manipulations. So for instance, these agents become less prone or less sensitive to changes in color or changes in very specific morphology. So it's sensations if the semantics of the environment stay the same. Arthur already mentioned we're very interested in gastronomy. For us, this is a challenging AI problem, specifically for the reasons that I already mentioned to some extent. So we have very diverse data sets that are large, in some cases also small, that are evolving, they're incomplete. There's lots of prior knowledge in ontologies and databases, but also in terms of domain expertise that we can get from humans. We have to deal with discrete and continuous data. You know, of course, sort of classification schemes might be discrete, but we also deal with human judgments, human perception judgments that might be more continuous, or also sensor measurements, visual, but also from novel sensors and sort of like e-nose and e-taste sensors that are coming on market right now. And then lastly, also what I already mentioned, for us, it's very important to do sort of recommendations, but that are creative. So it doesn't really help. It's probably a good recommendation for a chef if you say to add salt, but it's also very boring. So this sort of like take on what does it mean to create something novel, which is also out of distribution in some sense, that for us is best addressed. So like the hypothesis that we can address this with neurosymbolic systems. And so we're building AI systems that help in this process of discovery. And that can mean sort of different levels. So we're interested in ingredient pairings, completing recipes, but also predicting tastes and flavors of recipes. Just to give you a sense of how this works. So there are, for instance, many different hypotheses about how people innovate in this space. One is this food pairing hypothesis, where people have proposed that ingredients that share flavor compounds, that these ingredients go well together. And the classic example here is white chocolate and caviar, which has been proposed by a famous UK chef, and they share a trimethylamine. And so this is one of the strategies. And we've actually used neurosymbolic systems on graphs to capture some of those strategies, but also try to extract from data some of those strategies. And you know, this is just one of those examples where we use kind of bipartite graphs that link ingredients to the molecules that are constituents of these ingredients. And then we do neurosymbolic learning and reasoning on these in order to come up with new links in the graph, so kind of ingredient pairing. And then Arthur already mentioned it, there's a poster at the conference that also describes one of the systems that we built that where we can basically query some of this data in the food domain, where we build specific predicates and then also extend LTN to be able to work with these fuzzy predicates that are modeled around descriptive statistics that then allow us to address certain questions, such as what cereal product is not high in calories. And this is one of the results of this work. This is actually a collaboration with one of the chefs that we're working with, who took one of the systems that we built and created this dish from the recommendations that came out of this. So this is a dish that combines camembert cheese and sea urchin, and as an additional kinds of structure. And so, I mean, maybe this is a neurosymbolic dish. Finally, to conclude, I did want to mention another application area that it's sort of similar in structure if you think about how we model the domain and how we approach it in terms of the systems that we're building. And this is biomedical, so we're very interested in biomedical discovery. And again, sort of the main hypothesis here is that we can use AI systems in order to aid in discovery, and specifically neurosymbolic systems. So we're building these large graphs from papers, but also from experimental data, where concepts such as genes or proteins are linked in a specific way because they co-occur in papers or they appear in certain relations together. And then we train on these graphs that are of course evolving over time, that represent the knowledge that we have about the biomedical domain at a specific point in time. And then we try to predict discoveries in the future. And since I'm running out of time, I'm just going to mention a few papers here. So we had some results of this in NeurIPS, but also recently published in TKDE. And thanks so much for your interest. And if you're interested in applying neurosymbolic AI to problems like this, then please talk to us.
Thank you so much, Michael, and eat well. And so, yeah, I didn't know neurosymbolic computing can be delicious now. So that's
right.
Going to be my motto. Thank you. We'll come back to that. Very exciting stuff. The next speaker is Dan Phillips. Dan is head of Rothko investment strategies. He has a PhD in continual learning applied to investment decisions. And he's going to tell us all about death by XAI in finance. Thank you so much, Dan.
Yeah, apologies for the title, everyone. Yeah, my name's Dan Phillips. Thanks very much for the introduction, Artur. So I've been using machine learning, artificial intelligence to drive investment strategies for institutional investment products over the last 20 years. The next 10 minutes, I'm going to squeeze in a bit of context about XAI interpretability and really compressing the last few years worth of research journeys into 10 minutes. So finance in particular, investment management, it's become clear that if you can't explain your critical decisions, you're going to be in trouble, and that's true of many domains. The problem is that out of the box, explainable AI really isn't up to the job yet, and that means that using black box learners is pretty risky. We're going to look at two example approaches that we've dug into pretty deeply to drive investment strategies. Firstly, a complex black box approach, I guess you'd say, using continual learning, for which we've developed an XAI layer, and which was presented at the finance workshop at NeurIPS in 2019. Secondly, we're going to touch on a much more simple approach, an interpretable approach. It's symbolic, it's rules-based, which is going to be published in the Journal of Financial Data Science, the leading journal in my domain, next month. And the conclusion really is that more complexity can provide benefits, but it's almost certainly better to go for more simplistic approaches, Occam's razor. And all else equal, interpretable simplicity is always better than explainable complexity. So just some context, what's going on in finance may or may not be of interest to you, but there are certain parallels with other domains. There have been recent consultations, and the whole sector is playing catch up with many other areas of industry in that it's only now really rolling out machine learning across a wide range of functions. Consultations from regulatory and quasi-regulatory bodies have basically concluded that explainability is very important, but that explainability has to be in business language, language that you can talk to your clients in, your compliance officers in, and ultimately the regulator if necessary. and it's unclear whether surrogate models are going to be appropriate to do that. In other words, explainable AI, XAI, is going to be challenged. And on this slide are some worrying comments by these sort of regulators. And the one that sticks in my mind is that if you've got a black box model that needs explaining, and if your explanation is insufficient, those are my words, you could be exposing your firm and yourself to unacceptable levels of legal and regulatory risk. So the question really is adding complexity a sensible move, given that there's a risk that you won't be able to sufficiently explain your decisions when it comes to the crunch? So the two examples I'm going to go into, one more complex and one less complex. The first one using continual learning to drive investment strategy. So the advantages are the return characteristics are very good. So for pension strategies, charitable foundations or whatever, using a strategy like this to drive your equities allocations can be very good. You can also explain the memory functions, and I'll explain later what I'm meaning by that. But the disadvantage is its outright complexity. So what is continual learning applied to investment management? Well, the idea is that past events should be remembered by your investment models, and if similar situations occur again, knowledge of those past events should be used to influence decision making in the present. That's sort of what we're trying to get across here. In other words, we want to address the catastrophic forgetting of typical investment models. Continual learning augmentation, the approach that we developed, CLA, is applied to an existing investment model. So you take something you already have, and CLA augments it with a knowledge base, an external memory structure, and the approach monitors the input data to the existing model for change points. It stores memories of significant past events and recalls those memories when history approximately repeats itself in the present. So you don't want your models forgetting about things like the global financial crisis, the impact of currency crises, sovereign defaults or near sovereign defaults, and so on. And CLA is designed to store memories of these significant events and use this information to strengthen decision making in the present, given that past knowledge. So the external memory structure, and this is a depiction of it, is able to improve decision making in this way. The slide shows how the approach works in a trading simulation in emerging market equities in this case. So we're selecting individual names in emerging market equities. And it starts off with $1 invested way back in 2003, and it shows you, how that dollar has grown over time. The brown line shows a simple model, in this case, a feed-forward neural network. It's pretty basic, and it does okay. The blue line shows that same model augmented with CLA's memory structure, and the results are way better. So you end up with far more of a return at the end. The expanding triangle at the bottom shows how CLA stores and recalls memories over time, and each step forward in time presents an opportunity to store a new memory. So hence the expanding triangle as time steps forward from 2003 onwards. You can see from the horizontal blue lines here, just about perhaps, where memories have been recalled and used to shape investment decisions. And one important example is this example in 2009. It was a memory that was stored in 2009 and then recalled at 3 subsequent events over time. So 2009 is significant because it's the period after and including the global financial crisis, where central banks were heavily injecting capital into the global financial system. And you can see from the visualization that this memory was recalled in 2 particularly important periods over the Eurozone crisis and also financial crisis in China, where in both cases the threat or the action of central bank money in a similar fashion to 2009 arguably happened, and you can see from the blue line this very much aided the investment returns. So the conclusion is that a complex system that can be explained to some extent, but these explanations themselves need an explanation, and therefore there exists a risk that the given explanation isn't going to satisfy your stakeholders. The second option is to use a much more simple model, symbolic alternative, in this case a rules-based investment approach. And the advantages of the system are that the return characteristics also turn out to be good, but it's interpretable. So this representation shows how the system works, and it's taken from our upcoming publication, the Journal of Financial Data Science, as I say, which is being published next month. We're using a really simple a priori based approach to propose rule sets, which is sort of depicted here. We're valuing each rule set and selecting the ones that will give us the best results. And finally, we're applying these rules to the data, selecting stocks with good characteristics. The return characteristics are reasonably striking. The returns are excellent, outperform traditional quantitative finance models. And what we're showing here is that as you add additional input data items, the blue bar, the returns generated by this approach get better and better, whereas traditional finance models tend to peak and tail off if you give them too much data in practice, given the returns that they might generate. So in conclusion, an interpretable symbolic approach can prove very powerful indeed if it's built in the right way. And this means that the conventional payoff of accuracy versus interpretability you can see on the left, where the more interpretable a model is, the less accurate it might be, is a bit of a fallacy, specifically in finance at least. And the reality is probably more like what you see on the right-hand side, where interpretability and accuracy are basically, to a large extent, unrelated. The bottom line is that if you lose a bit of accuracy for a dramatic fall-off in business risk, and this is really my point, I personally would always take the lower risk approach. The overall conclusion is that if you put together simple interpretable approaches with more comparable, more powerful, complex approaches, this is probably the best way to go in many senses. But if you have to choose one or the other, interpretable simplicity is definitely the way to go. But the combination of the two, the neurosymbolic approach is definitely the answer in the longer run. So connectionist benefits and the benefits of a symbolic approach, the ideal for sure, and clearly inspired by our very own Professor Garces himself. So thanks very much for your time, and that's all I've got.
Thank you so much. Thank you, Dan. Perfect timing. I appreciate that. And yeah, exciting discussion on various aspects of XAI and whether, in a situation where a simpler system may be used and perform better, then you shouldn't be going for the more complex one, indeed. So we'll come back to that. Now the next speaker is Joe Townsend. Joe is a principal researcher at Fujitsu Research Europe. I'm pleased to announce also a collaboration that just started between City, University of London, the Data Science Institute, and Fujitsu Research, Trusted AI Project, Research Center for AI Ethics in Japan. And Joe is going to talk about toward Trusted AI rule-based explanations of CNN behavior. Thank you, Joe.
Oh, hello, are you hearing me now? Yep. Okay, good. So thank you for the introduction. Sorry, let's get my notes. Yes, so I'm a principal researcher at Fujitsu. So we have laboratories worldwide in, oh dear, it's brave. So in China, US, and of course Europe, which is where, and Japan and Europe, which is where I'm based. So as also mentioned, we've started this research center for AI ethics. This is broken down into two kind of smaller projects. So there's the Human Collaborative AI project, which is kind of largely about defining what it means for AI to be ethical, and then we also have the Trusted AI project, which is really more about implementing the technologies which adhere to these standards that we define or enable them. So if we need to trust AI, then we need to trust, that includes trusting our neural networks. So neurosymbolic research nicely fits in under this topic of trusted AI. So in this talk, I'll be demonstrating an application of ERIC, which is our method for extracting explanations from a trained CNN, originally presented at ACCV last year. There isn't time to go into detail about how the method worked, but the basic tuple is that we map the outputs of kernels to binary values through a quantization function, which thresholds the L1 or L2 norm, and then we use a tree extraction method to map these features to the network output. which so I'll direct you to my colleague Theo's talk in about an hour's time. But in summary, EVP helps us to train kernels to make it easier to interpret what an individual kernel sees. Straight. We are looking at multiple potential applications, but in this scenario, we're looking at like say the self-driving car or ADAS system, or rather the image recognition component in such systems. And we'll be trying to classify the traffic sign or the larger scene, the scene that the car is currently in. Because classifying either could have potential fatal consequence such a situation occurs. So for example, if a car is driving at 70 miles an hour in a residential area, diagnostics identify that the image recognition component was at fault, then we need to sort of explore why that was. So I'm bravely going to try and do this demo live. I have backup slides if it doesn't work. Oops. Okay, that's already not working. Here we go. Yeah. So here we see we have this town center scene. So like where we're reviewing footage that can be seen through a dash cam, and the camera has already identified a traffic sign warning that the road is going to become narrow. On the right is the CNN's correct classification of the narrow warning sign, and an explanation that Eric has provided, where each of these words corresponds to a kernel, or rather what a kernel sees, and these labels are currently assigned manually, with the idea of future of hopefully finding a way to label these automatically. So the software enables a developer to inspect the kernel, ideally. Okay, no, that's not working. Okay, back up. Oh no, it's just, yeah. So each of these corresponds to a kernel. We can click on one of these links, and yeah. So we have this view of, in this case, the top 10 images which most strongly activate the kernel according to the L1 or L2 norm. On the right is the output of the kernel directly, and then we use that to make a mask. And these are purely for inspection purposes. They do not have any effect on the actual classification. So in this case, the black curve kernel is reacting to vaguely curved shaped things such as the zero or the bump, and of course, in this case, the sort of bend in these two parallel lines. But there's an interesting example. If we go to, actually, I'm going to just use the slides for this now. If we go to this example of a speed bump, we get something interesting. So again, the classification is correct, but and once again, we've got the black curve as part of the explanation. But interestingly, the kernel also picks up on this combination of the red and the blue. So this is what the kernel is seeing. It's reacting to these situations where red and blue appear together in the same scene. And in this case, this is actually accurate with respect to the training data, because whenever these traffic signs appear, then in this particular data set, there's always a speed, like a distance indicator next to the sign, which is blue. So this is not how a human would classify this sign. We would use the combination of the triangle and the bump. If we don't really even need the triangle. But the point is that we have used Eric to identify a situation where the CNN is correct, but for the wrong reason. I'm also going to show example of when a scene is classified. In this case, we've got this is a town center. So we're classifying scenes as one of town center, or a suburb, like a residential area, or a main road. And by main road, I mean something like a motorway or a highway or some high-speed environment. Here, one of the kernels reacts to brick patterns. So these are evident obviously in the buildings, but also in the roads. You can see that there is a brick pattern in the road itself. So this is a fairly reasonable feature to use to identify a town center, because the buildings will always be close, and in this data set, the road seems to have this pattern. But in another example of a misclassification, where this narrow tunnel has been mistaken for a main road. So if the car was making its decisions on this information, it probably wouldn't in reality, but the point is, if it decided to go at a speed that would be allowed in the main road, like 70 miles an hour, it might cause an accident because this is a very narrow tunnel. And we can use the rule inspection tool, which is similar to the kernel inspection tool. We see the top 10 images which activate this rule, and they're all similar in the sense that they're long and narrow, with very few markings in the road. But the major difference is there is no wall in these images, where there is here. But we know that the kernel the CNN detects walls. So we might want to redefine this rule to consider the presence or absence of the brick wall, and then perhaps use this information to retrain the network. But this is something that we have not yet implemented. Sorry, there's not time for that stuff. So yeah, the putting the rule back into the network is more of is really about closing the neurosymbolic cycle of CNNs, and this is something we've not yet done, or otherwise using that information to retrain the CNN. So other activities that we're doing are we're hoping to find other applications, such as that perhaps
Can you guys hear Joe? I
No,
think we lost him. Yeah,
we lost him.
I think we lost him at the right time. So so that's the concluding. Oh, hi Joe, you're back. We just lost you for a bit, but I think you were just wrapping up. So
okay.
I think that's great. We've seen the topics there. Well, we can come back to that in the discussion. Sure. Thanks very much for that. It's very challenging doing a presentation and a demo in a 10 minutes. So well done for that. Right. So the next speaker is Alex Jaimes, Chief Scientist and Senior Vice President of AI at Dataminr. Just had a very successful investment round. And also, you just announced your advisory role to the Colombian government on AI strategy. So exciting stuff. Thank you, Alex, for waking up at 6 a.m. for this.
Thank you. Happy to be here. So I only have 10 minutes, so obviously it's going to be very quick. So I want to talk about AI in public data for humanitarian and emergency response. And I'm going to do this in 5 parts. It's quite a bit of information, and I'll go fast, but hopefully I'll get to most of it. So let's start with context and what it is that we do and how this area of neurosymbolic is relevant to us and why I think it's so exciting, particularly in the kind of work that we do. Essentially what we do is we detect events from public data sources for 3 main verticals: corporate risk, news and journalism, public sector. So we monitor public data sources all over the world. That's text in multiple languages, formats, images, video, audio, sensor data, and combinations of all of these to detect important events. And then we send out alerts to customers in those 3 verticals. So there are all kinds of companies and all kinds of industries, as well as public sector for emergency response. So to give you examples of the applications in terms of humanitarian response, we've partnered with the UN so they can use our products for free, and they basically use them to keep UN personnel safe all over the world. So to give you an idea of the scale of this, about 20,000 UN personnel all over the world, which includes civilians, experts on mission, police, et cetera, et cetera. And so they want to know about any events that impact their safety and the safety of refugees and so on and so forth. And Just recently, we've seen a lot of activity in Afghanistan, and you can read about it in our blog post from September 21st, where the information we provided was used for evacuations and so on and so forth. So that's one. The second one is emergence response. And some of that is at a smaller scale, some of it is at a larger scale. But when most of us think about the disasters, we typically think only of the big ones, right? We think of the hurricanes and so on, and the earthquakes. When you look at the Red Cross list of types of disaster, you see that the list is actually very long. And there are some that we don't really think about too much, like water safety, right? And then pandemics, we were not thinking about pandemics until COVID, but there are many, many different kinds of events. And so the events we report on include many of these. And of course, we've been covering COVID. We actually sent out the first alerts on COVID back in December of 2019, right when it was starting. I hope I'm not mixing up the years. And when you think of these important events, it turns out they happen all over the world all the time, right? Most of us kind of tend to think that they only happen once in a while in certain locations. When you look at the maps of disasters and major events, they're happening all the time, all over the world. That includes wildfires, all kinds of violent events, riots, protests. And when you get to a more granular level, at the city level, things like traffic accidents are continuous, right? And they're rare, but they're not. And so there are smaller scale emergencies on the physical front, traffic accidents, shootings, explosions, fallen trees, you name it, right? Things that affect day-to-day living that are not necessarily all of them on the news, some of them are. And then cyber has become a pretty big one. And I expect it to increase very significantly in the coming years. We have ransomware attacks, expired certificates, data leaks, phishing. So a lot of this is relevant to both governments and corporations and corporate risk. And you'll probably all remember the Colonial Pipeline attack. And obviously the impact of these cyber attacks is really, really significant because it spans huge areas and can impact consumers, the economy, and governments, and many, many people. So when you think of social media, that's just one of the buckets. I mentioned sensor data, I mentioned web, there's also dark web. We monitor all of that as long as it's public. If we look at just Sandy, which is back in 2013, about 20 million tweets were sent. So a lot of information about disasters is being posted publicly. So in practice, how does this work? We have this platform that processes billions of data points per day, social media blogs, media sources, sensors, et cetera, et cetera. We essentially want to determine what I call the 6 Ws. Is it an event or not? Where, when, how, is it new, et cetera, et cetera. And then once we identify the events, we automatically summarize that event. And that's what you get as an alert. And we send it out to customers. So there's a recommendation component to it and so on and so forth. So in practice, the platform includes ensembles of many different models, combining many different technical approaches for detecting these events and for summarizing and generating them. So it's very complex. And I want to point out one minor box here, which is knowledge. And that now you can see, if you look at this graph, this diagram, you can clearly see why neurosymbolic is kind of the way to go, right? Because we use a lot of deep learning, a lot of symbolic type of work. And so complex and simple models, knowledge in many places, fast and slow models, computational cost-efficient models first. And usually the goals are to improve accuracy and reduce noise and costs, right? At this scale, you have to think about costs. So we have to continuously monitor the models and collect feedback. So what are the main challenges? Complexity of disasters. Each disaster, it's its own monster. They're all different, even of the same type. 2 hurricanes are never exactly the same, which is why it's so hard to predict them. And then unexpected events will often make a disaster something completely different from what it was what was modeled that it would do. Information is fragmented. The events come at different speeds. Geographic spread varies significantly. You need to efficiently deploy resources and logistics to address these disasters. And so with each type of disaster, and depending on who you're talking to, the vocabulary is different. Again, the scope and scale, the time, scope and scale, the strengths of signals, and then what's important, who's affected, where and why. Causality is really critical. So what we call the aftershocks. So you look at temporal and spatial distribution. A terrorist attack somewhere may kill only one person, but it could have significant political implications. A hurricane has a huge geographic spread, so that's an earthquake. And so one of the things we've been looking at is cascading networks and knowledge and how causality falls into this, and combining semi-supervised methods with supervised methods and unsupervised methods. So in terms of detection, wide range of events for small traffic accidents or statements, political statement is very important. It can move markets, it can do all kinds of things. So they require lots of context. Trillions of events, clustering, causality, I mentioned it before, concept drift, concept lifting are critical in terms of summarization, because once you identify the event or family of events, what do you actually send to your customer? What do you send to a first responder? You can't send everything, you need to summarize it. So how much detail is enough? What's important, what's not? And then something that we don't usually talk about in neurosymbolic system is the HCI component. And that's really, really critical. So we have domain experts, and we want to extract as much domain knowledge from them and manage that knowledge. And that's critical. So in essence, I think this is the hardest problem of AI, which is really the value of information in real time. And then, so in terms of future directions, and it's just one slide, but it's really dense. So everything that has to do with knowledge graphs and knowledge bases, causal knowledge graphs, semi-automatic and automatic construction, ingestion, and maintenance, again, human in the loop, graph neural networks, combining unsupervised and supervised, which is not the same as semi-supervised, and semi-supervised by itself is also really critical. Reasoning for detection and response management and planning. And then that's on top of all the standard challenges in NLP, computer vision, multimodal anomaly detection. And the bottom line is extraction of very basic semantic information is still very, very hard. And so linking and knowledge graphs are not enough. Linking of all this knowledge and all these events. And then finally, optimization at scale in every way, shape, and form. So that's it. We're hiring, we publish in all kinds of places, and happy to continue the conversation.
Great. Thank you so much, Alex. Yeah, that's fascinating stuff, really. The scale of it and the value. Yeah, thank you very much. The last but not least speaker is Dragos Margineantu. Thank you so much for also waking up at an unacceptable time. Dragos is AI Chief Technologist at Boeing Research and Technology. He's a long-term contributor to the NeSy workshop series, has given keynotes in the past. He's also a very well-known machine learning researcher. Thank you so much, Dragos, for giving this talk. I assume it will include autonomous taxiing airplanes.
Well, it includes that. I have a problem here with sharing. 1 second.
Right.
Okay. Should be.
Hello, can you hear me?
Yeah.
I am Faye from the technical support. Can I help you? This is great.
I'm fine.
Okay, this is great.
Okay. Can you see my slides?
Yeah, all good. Thank you, Dragos.
Okay. So I want to talk quickly about fundamental ideas in architecting decision systems for business. As Artur mentioned, I'm a machine learning person, but in the last 5 to 7 years, I've been deeply involved in architecting and deploying decision systems at scale. And as a machine learning person, probably 10 years ago, I thought that just thinking in isolation about learning is all that matters. Well, typical decision system architectures include, and all of you who have deployed this, they have some control component, prediction component, perception component, speech recognition, inference, and so on. And in virtually all of these, when we deploy, we have learned models. And but we have no books and no rules on where those learned models are and what functions those models learn. One thing that's essential is that these decision systems have to act without having a complete model of the world. We know that we care about way more than accuracy, and what we care about is handling unmodeled phenomena. All of you who deploy systems, you know that you care about that example or that instance or that region of the space that you haven't seen in training. Therefore, having self-estimates of competence is required, and we'll talk about the hierarchical decomposition of the decision space. So first of all, what do we do about the learned models? So this would be the connectionist problem that I want to talk. And one inspiration is the Alvin system, the No Hands Across America system, which was steering a car almost 30 years ago from Pittsburgh to DC to San Diego. And if you read the paper, actually hidden there is that the neural network wasn't only having a prediction of the steering, but it was predicting the output image. It was actually predicting how competent the network is. And if you read virtually every paper on a deployed system, you'll see that those systems actually don't do just a prediction or an estimation, but they have a component that relates to estimating the risk and on how competent the system is. So that's why in my team and actually in Boeing, we actually impose that learned models don't do only predictions. And I would like to do this throughout the research community. Just a prediction of a class and so on is less and less important if you care about deploying. You have to have an output on some sort of competence, and most of you know how to do it from your favorite learned model. We know how to do it from neural networks, from decision trees, from SVMs, and so on. But that's essential, and it's essential simply because if we care about robustness, we care about an area of competence of the model and having guarantees in that area. We will never, no practical application will ask you to be competent in the entire decision space. And meanwhile, all the anecdotes about machine learning are basically about having a model that tries to predict in a region where it didn't have any data or where somebody hasn't thought about. So think about that. And the way we use this is actually twofold. One, at design time, it allows, if you do it right, it allows you to select competence regions and so to grow organically the competence regions through generating more data, querying data, active learning, you name it. At runtime, it simply minimizes risk. Just saying, I don't know, actually allowed us to make great advances with regulators, for example. Humans do say, I don't know, when we're not competent in an area. So that's one thing. And then the full end-to-end decision system, when I started working on autonomous systems, I looked around and basically implemented a decision backbone based on papers that were written back in the 80s and 90s. And then we started talking to autonomous cars companies, Waymo, Uber, and so on. And basically everyone building autonomous systems has a decision backbone that looks like this. It's a hierarchical planner architecture from high-level decisions. Think of what you're gonna do tonight, having dinner with family, buying something, to low-level, high-frequency planning and control. This is what you have as a backbone of every decision system, and more so, even if you think beyond autonomous systems, any decision system has a backbone that looks like this. How is it? Well, first of all, it's decomposed hierarchically because of computational complexity reasons. And around it, we have the perception on one side, you name it, whatever perception you have, dialogue with the humans and so on. And on the other side, we have the knowledge bases and the physical models and common sense knowledge and so on. It's very important also to think about that at low level, high frequencies, we care about some sort of fault tolerance. In every system, in finance, autonomous systems, you name it, you care about some fault tolerance. So one thing I want you to walk away from here is to notice that we decompose these from high from high dimensionality, low frequency decisions into high frequency, low dimensionality. And that's for computational complexity and for robustness. Vice versa, as we go higher, it's lower frequency and higher dimensionality, super essential. And I'd like to invite you, whenever you think about your favorite area, explainability and so on, to think about the frequency of decisions. And think about that, probably you will not need explainability at lower levels, but you need it at higher levels. And I'd like you to think about who consumes your decisions. Again, this is something that autonomous systems do. Now, for this meeting, right now, all these systems are heavy neuro on the perception side, symbolic in virtually all the rest, and neural or symbolic in the control side. One other thing that we do about, and that I would like to propose for everything, is to be inspired by Minsky's quote that you don't really understand something if you only understand it one way. The strength of neurosymbolic is basically to provide a multifaceted understanding of tasks, and that provides robustness. Right now, virtually on every task, we do it only one way. We have our favorite learner, we have our favorite predictor for doing it in one way. When we deploy systems, actually, we care about doing things multiple ways, and that's why we care about explaining something that was done in a way and so on. Discussion conclusion: robustness should be at the center of thinking in decision systems, even if the decisions are lower risk. It's driving the architecting and the thinking about machine learning and about the full decision systems. I talked to you about a couple of ideas here, but bigger than that, the corollary. So the practical approaches in decision systems are driven by the computational complexity, and that's why we decompose these spaces the way we talked about. Risk minimization for unmodeled phenomena is at the center and should be at the center of our thinking. And then the thinking and the driving of the approaches should be driven, as I mentioned, by two big things: the frequency of the decisions. So your output, when you learn a model, think of how frequent those decisions are consumed, and by the entity that consumes them. Is it a human? Is it an expert? Is it another system? And that will answer many of your questions that you may have. So that being said, I think my time is up.
Thank you. Thank you so much. Yes, very interesting to see these developments literally across the world. And I was thinking about one question to kind of try and connect the different perspectives and the different application areas. And I just put out a paper on accountability in AI, and I'll put the link there in the chat. And like Dragos mentioned, as a researcher, we tend to focus on our very specific area. And I thought for many years that explainability was going to solve all the problems. But then when writing this paper on accountability, there are these 5 components: beneficence, non-maleficence, autonomy, justice, and explicability. And all of these seem to be very topical if you think about the latest Facebook scandal and the whistleblower in the US Senate recently. So from this broader perspective of accountability, I wanted to ask you guys, what is your take on this? Is it something that if you operate more like a research lab, you don't need to think too much about it, or is it something that is in your mind once a month or every week or every day? Because you know, how impacting are these from a practical perspective, these aspects of accountability? Who would like to take a shot on that?
I think it's essential. So it's essential to think about the risk of the decisions. Even if you're a researcher working narrowly on your favorite model, whatever it is. Frankly, at this point, I don't even know how to integrate a model that just produces predictions without those self-competences because of that. And also another thing to think about is no matter what we develop AI autonomous, what we do is actually we change the contract with the humans. There is a human that consumes whatever it is, even in autonomous cars, autonomous airplanes, whatever, it's going to be different. And it's essential to think about that interface and the risk of the decisions that result from that interface. Just to give it in airplanes, we have worked on the interface between pilots and the airplane for almost 100 years. So by building autonomous systems, we'll change those interfaces, and we have to think very carefully about them. And risk is essential.
Yeah, I just want to add that I totally agree with Dragos, and we do the same thing in terms of, you know, the competence of the models. And so by definition, every model builder needs to think about the consequences and the cost of errors. You can't just not worry about it. It has to be an intrinsic part of what you do, and it's part of the evaluation. And I think Dragos said it as well. The evaluation is continuous. It doesn't stop once you deploy it. You need to continue monitoring and modifying the model because things change.
Yeah, I completely agree with both Alex and Dragos. You know, and the sentiment of your question, Artur. You know, I mean, I guess it depends on the domain in terms of the magnitude of the decisions you're making. If you're, you know, making high magnitude, a small number of high magnitude decisions, then the onus on interpretability and these things has got to be much higher. But under all circumstances, you know, you have to be assured of the basis of the decisions that are being made by the models or recommendations being made by the models. And a way of monitoring the causality, basically, ultimately.
Thank you. Michael, do you worry about accountability every week, every day?
Yes. In fact, sorry. Yes, specifically also because in large companies like Sony also, there's a lot of deployment of models. And there are large parts of the company that are working on machine learning models and deploying them in different applications. So it is something that we worry about a lot, actually. Yeah, I don't think I have anything specific to add to what's already been said. I mean, all the things, and this makes it very complicated, right? So you have to think not just like building the model, doing the research, building the models, and then deployment. I mean, in all those parts, you need to make sure that actually you also have the right stakeholders in place, because I think it's quite a lot to put on the researchers and the engineers. Of course, we need to train them better to be at least aware of these issues. But in many ways, the systems we are building are actually impacting people that are outside of our community, including, you know, I'm basically talking about diversity. So people that maybe don't have computer science degrees because they're like underrepresented in the field and so on. And that's where it becomes challenging, I think, because we have to make sure that these voices are part of the process. Basically, if you don't have the experience of how this might affect somebody, and that's normal because you don't, you know, you're not in that community, I think that really creates issues. And how we do that in an industrial setting, I think, is one of the key things for us that we worry about every day. And I don't think we have good answers, though.
It's a huge issue and very broad. And yeah, like I said, I used to focus on explainability as the solution to. So I used to focus on explainability as a set of rules, and now I can see all the different dimensions of explainability, and then even beyond that, aspects of fairness and ultimately accountability and trust. Joe, would you like to add anything?
I think one question that comes to my mind often is, who is the explanation really for? So the example I gave, like okay, this is telling you why this CNN has made this decision of misclassified this sign and caused this accident. But if that's good enough for the developer, but even if it satisfies me, actually, I still don't know how the rest of the car works. Like, there's still a lot I don't know. And why? And I ask, why do I trust the car? Well, I trust it because I trust my mechanic who's done the MOT. And I think someone, and I was thinking, why do we use a lot of things without knowing why they work? So we don't have explainable planes, we don't have explainable cars, but we trust the authorities that regulate them. And so the inexplainable AI, are we looking to extract rules which are good enough for the regulators, or do we need it for the actual user of the software? Because there's so much technology that we use day to day that, well, we don't ask for explanations for.
Can I just add one thing to this whole discussion, which is that it's become very clear to us also that some of the goals that we have in this space are actually contradictory. So, for instance, if you want to address fairness in models, you're going to have to know, for instance, about protected attributes of some of your population, and that goes against privacy. So there, I think we're starting to see these problems where this is really societal, right? Like, how do we trade off some of those? Or actually, we shouldn't trade them off. Like, I mean, how do we deal with those kind of inherent conflicts in some of the goals that we might have in addressing things around AI systems?
I'd like to add one thing. In thinking about the consumers of the decisions, I think we have an easier life in dealing with super experts. I'm happier to deal with pilots than with car drivers, and we all have to think about that. And among us, AI researchers and so on, it's we'll build a generation of researchers working on those interfaces, and the more stochastic the world of the decisions of the consumer, the harder the problem is. Air traffic controllers leave little room to, there's no joking, there's, and so on. Versus, let's say, your consumer credit card user or something who, may make, suboptimal decisions. We have to think about that, and we have to think about the drivers of the society, as mentioned. We have to model those in our systems.
Yeah, exactly. Thank you so much. Yeah, I guess, like you said, the contract is changing, and also, as Alex mentioned, the aspects of HCI and human robot and human machine interaction will become more and more important and need to be accounted for. Thank you so much again. We're running out of time. This was a great example of applications and industry uptake of neurosymbolic technology. It's great to see it happening. So thanks again, Michael, Alex, Joe, Dan, and Dragos. And I hope to see you face-to-face next year. Thank you all.
Thank you.
Yep.
Bye.
Bye.
This presentation, could you...
Yes, I'm here. I'm Theodoros Kashumis. Hi, everyone.
Hi, everyone. So you will be on the first speaker, okay?
Right.
All right, thank you. Do we have the second speaker? Okay, not yet. Okay. So anyway, so we're going to start in 1 minute. So you have 15 minutes questions included, and then we'll have the invited talk. So I'll give you 3 more minutes before the end of your presentation, so we make sure we get on track.
Right,
and
sure.
So you get started in 1 minute, and I'll do the introduction. So you can probably start sharing your screen.
All right, let me check.
Hi, Veronica. Yeah, okay. Yeah, we can see your screen.
Right.
Yeah. All right. So well, hi everybody. So thank you for joining this session on NeSy and Unexplainable AI. So that's a nice, clear 2021 session. And so today in this session, we have 2 papers. One will be presented by Theodoros, and then we'll have another presentation from Anna. So each paper's presentation has 15 minutes, 3 minutes of questions and answers included. And then we'll have a keynote presentation from Zachary Lipton after the 2 papers presentation. So Theodoros, the floor is yours. You can go ahead, and if you have questions, you can put it in the chat. So at least Theodoros and the other speakers can provide answers in the chat if time doesn't allow to have oral questions. So Theodoros, the floor is yours.
Okay, great. Thank you very much for the introduction. Hi, everyone. My name is Theodoros Kassiomis, and this is a joint work with Joe Townsend and Hiroya Inakoshi from Fujitsu Research of Europe. In this work, we present a method called Elite Backprop, EBP for short, to train more interpretable neural networks by inducing class-wise activation sparsity. After training, each class will be associated with a small set of elite filters that activate rarely and have strong activation magnitude on images from that particular class. The goal is to make more targeted filters that focus on specific concepts from a particular class by penalizing filters outside this elite. After training with EBP, we observed that filters tend to capture more compact and localized regions, which are more interpretable in general, and it is easier to assess their activation pattern. Our method is broadly applicable, and it does not require additional object part annotations during training. We also demonstrate that our method achieves high degrees of activation sparsity without accuracy loss, and enhances the performance of rule extraction algorithm that distills the knowledge from a CNN by inducing more compact rules that use fewer atoms in explanations and describe the decisions of the CNN while maintaining high fidelity compared to other approaches from the literature. Our motivation for this work comes from the following facts. In classic CNNs, a filter may fire in response to multiple object parts, and the activation region is generally noisy and large. This makes it hard to assess the activation pattern and hinders interpretability. Additionally, the increased number of weights and non-zero activations in CNNs leads to redundancy in representations in which different neurons co-activate on the same topic. This makes it more difficult to distill the model into a simple interpretable representations because the extracted rules are more verbose. And when it comes to explaining the decisions of a classifier, one can regard compact explanations as more interpretable because there is less information for the reader to assimilate. That being said, ideal explanation should contain only a handful of rules that reuse and combine primitive filters. Regarding background work, the field of neurosymbolic integration concerns both post hoc and self-interpretable models of explainability for neural networks, and employs symbolic representations such as decision trees or logic programs to explain the network's behavior. Another perpendicular line of research focuses on sparsifying activations in order to make the model more interpretable, since it has been hypothesized that sparsely activated neurons are more interpretable, or to prevent the co-adaptation of neurons in order to tackle the inherent redundancy in neural networks. Before explaining our method, let's introduce some preliminaries. We define the activation of a filter, Fj, as the special mean of the corresponding feature map. Essentially, any function that aggregates a 2D matrix into a single number could make sense here. For example, someone could use any p-norm or the maximum of the feature map. A filter is considered active if its activation is above a certain threshold theta. This threshold could be the mean of the filter activation over a set of images, or the standard deviation, or any other choice like a specific quantile from this distribution of activations. By quantization, we mean the process of aggregating and thresholding the feature map of a convolutional layer. We aim to tackle the aforementioned inefficiencies listed in the previous page by introducing an algorithm called a leadback prop that enforces class-wise activation sparsity. This means that our method will associate each class with a handful of elite filters that activate very rarely and have strong activation magnitude on images from that particular class. This is done as follows. During training, we accumulate filter activations in a list for each class separately. And after normalizing this list, we assign each filter a probability of being active for each class based on the frequency and the activation magnitude from images of that class during training. Then, for each class separately, filters are ranked and the top K filters form its elite. Filters that activate on images from a class that do not belong to its elite will be penalized, and the penalties will be inversely proportional to their ranking. This number K of that defines the number of elite essentially controls the degree of sparsity and the representation power of the model, more sparse for lower K values. We conduct experiments on 2 image classification datasets, a 6-class animal subset of Pascal Vogue and a toy 3-classed subset of Places 365 that consists of the classes Forest Road, Highway, and Street, in which we will refer to as road dataset for simplicity. We also compare our method with several activation sparsity methods from the literature in terms of the accuracy of the model, activation sparsity, and rule extraction. We saw that our method achieves a higher sparsity without sacrificing the accuracy of the model, and also the rules that are extracted from the CNN trained with EBP use fewer atoms and have higher fidelity compared with other solutions. We also perform a qualitative evaluation by visualizing the receptive field of filters trained with our method, and also the quality of the rule extracted. We conclude that filters trained with our method generally focus on more compact semantic regions and which are more interpretable and easier to assess the activation pattern. In the next slides, I will present the experiments and the results in more depth. So to assess the extent to which EBP benefits rule extraction by inducing parsimonious compositional representations that reuse and combine primitive filters, we saw that a binary decision tree that is trained as a symbolic approximation of a CNN is more compact when that CNN is trained with our method than without. To perform rule extraction, we first need to convert the output feature map of a convolutional layer into a binary value via a quantization function. And we approximate VG16 on the road dataset and Pascal by generating decision trees using the sklearn decision tree classifier and entropy criterion for splitting the nodes. The tree takes as input the thresholded filter activations of conv13 layer of VGG16 and as target the CNN's output classification. So for a given input instance, the induced decision path from the root to the leaf node of the tree provides a symbolic explanation of the original CNN's classification for that particular instance. The reason we extract from Conv13 is because deeper layers are known to represent more abstract concepts in general that can be related to object parts. For visualization purposes, we show a depth 3 tree on the right-hand side, and each path from the root to the leaf can be regarded as a separate rule over a set of atoms. For example, the first rule states that if filters 1, 6, and 5 are active, then the input is forest road. Similarly, if the second rule states that if filters 1 and 4 are active, while filter 6 is inactive, then the output is a highway, and so on. In this slide, we present some examples of extracted rules after training with our method using depth 3 for simplicity. For each filter, we also depict its highest receptive field of activation and the label below it. These labels are manually assigned based on the top 10 highest activated images for each filter and their corresponding receptive fields obtained from a forward pass during training. And we plan to automate this labeling process in the future, though. The green frame in the rules denotes the presence of a pattern, whereas the red frame denotes absence of a pattern. It is notice how a concept like trees and buildings in this slide are shared between classes, promoting compositionality. This slide depicts quantitative experiments on the raw dataset. We compare our method with 4 other relevant activation sparsity methods. In the first row, the scatter plots present the results after training VGG16 with its method, using different hyperparameters and then performing rule extraction. In the first column, we observe that after training the CNN with EBP, the model achieved comparable accuracy with other solutions, and in some cases higher than other prior arts, while realizing higher degrees of Hoyer activation sparsity. Similar results hold for other sparsity measures. The second column depicts that the program extracted from the CNN trained with our method has higher fidelity, while realizing higher degrees of activation sparsity, whereas this third column shows that the extracted program trained with our method uses fewer unique atoms and rules in the explanations compared to other approaches. The number of atoms essentially measure how compact the representations are and how compact how compact the explanations are. Fewer atoms implies that fewer unique filters are used in explanations. Therefore, those explanations are more compact and less verbose. And the table on the bottom side depicts that our method achieves high activity sparsity across different activity sparsity measures, and the program extracted from the CNN trained with our method has higher fidelity and uses fewer rules.
Dragos, you have 2 more minutes to go.
All right, thank you. This slide shows the receptive field of filters trained with our method and how they capture more compact localized semantic regions. And the following slide depicts the evolution of a filter trained with our method. Before applying EBP, the filter filed a response to traffic signs and trees, essentially capturing both concepts. And the histogram on the right side shows how the probability of the filter activation is spread between these classes. And after training with our method, the filter fires in response to traffic signs only, which are present mostly in highway and street classes. And that's why the probability of those classes has been boosted in the orange histogram. So in conclusion, this paper we proposed a method that induces class-wise activation sparsity to encourage more parsimonious and interpretable representations. And our conclusions for the experimental evaluation on 2 datasets is that our method can realize high degrees of activation sparsity without sacrificing the accuracy of the model. It can benefit rule extraction algorithm that distills the knowledge from the CNN, as fewer atoms are used in explanations. while maintaining high fidelity, and it encourages compositionality by reducing and combining primitive filters. In future work, we aim to conduct experiments with different values of K for each class and further analysis of role extraction on different layers. And another future direction is to embed rules into neural networks in order to enhance their interpretability and generalization capabilities. This rule embedding can assist in neural symbolic integration, which is a quite important step towards bridging the gap between neural networks and symbolic representations. So these are the references used in the slides. And thank you very much for listening.
Thank you so much. That was a great talk. So time is getting towards the end of your talk. So we may have time for one question, but the answer will need to be in the chat. Do we have any question? So I have a question on the compositionality of filters. Did you try to figure out if filters could be clustered based on some kind of representations, and if you try to analyze the kind of the semantics of the filters? But to those, if you could answer my questions on the chat, because we need to move to the second talk.
Yes, sure.
Yeah,
Thank you.
Yes. Thank you, Theodoros. So now we move to the second talk. So Theodoros, if you could unshare your slides. And I think Anna, you just joined the session. So if you Anna, you're the speaker, you can get your slide shares. So again, thank you for joining the NeSy and XAI sessions of IJCLR 2021. That's the second paper's presentation before the invited talk. And this paper is on a new concept for explaining graph neural network. So Anna, you have 15 minutes, questions included. So Anna, you can start sharing your slides. And I'll give you a warning 3 minutes before the end of your talk, but that means you have you have 3 minutes for question and answers, or you can rush towards the end, but that means no really questions if you reach the end. So now over to you.
Okay, thank you, Freddie. Yeah, hello, I'm Anna, and I'm going to present our work, a new concept for explaining graph neural networks. So our work is about explainability on graph neural networks, and we chose GNNs because many important real-world data sets are graphs or networks, like social networks, knowledge graphs, the World Wide Web, and many more. And while graph neural networks leverage link structure to encode information as well as incorporate node feature information and currently achieve state-of-the-art on many prediction tasks, they do lack transparency in their decision-making like many other connectionist models. And a number of subsymbolic approaches have been developed to provide insights into the GNN decision-makings, mainly perturbation-based approaches, which then output a mask, edge mask, or feature masks with the most important or influential features. And while these are first important steps on the way to explainability, the generated explanations are often hard to understand for users that are not AI experts. So our approach targets experts of the application domain. Explainable AI and visits the widespread application of AI models should be more likely to succeed if the evaluation of these models is focused more on the needs of the user. And a common weakness among these subsymbolic approaches is the user's responsibility for compiling and comprehending the symbols in the final step, often relying on their own implicit form of knowledge and reasoning about them. And how the input, output, and the emitted symbols relate to each other is often an implicit cognitive intuition on the user side. So in this position paper, we address the weakness of those approaches or this specific weakness by proposing a post-processing rule-based companion to such a subsymbolic explainer method. And thereby we want to complement the subsymbolic instance level explanations with model level rules. So by extracting and aggregating global rule-based explanation through a standard white box machine learning method from the generated explainer subgraphs. By explainer subgraphs, I'm talking about these explainer masks that often visualize a smaller subgraph than the original input graph. We reduce the amount of additional interpretation needed by the user and provide a model level explanation that captures explanations about the global behavior of a model by investigating what input patterns can lead to a specific prediction. And as an example of such an approach, we developed a method we call Subgregs, where we take the output of the state-of-the-art explainer method as input, as well as graph-specific attributes, such as node distances and network motifs, and use decision trees as our white box model to generate rule-based explanations. And here you see the conceptual schema of this approach. And the goal is to generate systems that can provide model level rule-based explanations which don't rely on the user's understanding of the domain, where we try to achieve this by combining the results of a subsymbolic explainer method with a white box rule generator, which then should satisfy the representation needs for human comprehensibility and reasoning. And this rule-based explanation generation isn't a standalone approach, but an add-on post-processing method in order to enhance the explanations and make them more user-centric. So after training a graph neural network, you have an input graph, you train your graph neural network. The graph neural network's decision-making process is interpreted by identifying a sparse receptive field containing influential elements, so a mask. And our post-processing approach consists of taking these initial symbolic explanations and lifting them to the level of rules. So you can see here the process of generating rule-based explanation for a node classification task, where we have an edge mask and a node feature mask that are generated by the subsymbolic explainer model, and then F, and then subsequently rules for edge and node features are created by the white box models D. And the rules are created through a classification process where the individual edges and features are assigned binary labels, influential or not influential, based on their masking value. And the white box model is trained using those binary masks as the target variable. The generated rules then function as a model level explanation for the respective classes of the original classification problem, and furthermore introduce a verbalization element that can make explanation more comprehensible for the user. An important part of generating a user-centric explanation is to make the explanation customizable and include provenance, for example, by including information about the domain knowledge utilized by the system to increase user understandability and also acceptability. Such domain knowledge can be included by extracting attributes from subgraphs, depending on the domain and classification task. An example here of such inclusion of domain knowledge are graph-specific attributes, such as motifs, are mapped to the domain language. And in a more formalized setting, now here we are working with decision trees, but we've also started to work with more formalized semantic web techniques. Relational rules could also be included, for example, to represent domain-specific constraints. So to test this conceptual approach, we propose our Subgreg models, which enables the generation of model level explanation. So here on the left side, you can see a input graph with a target node. So we are looking at node classification here, but could also be graph classification. And then we have the subsymbolic explainer which identifies the important edges and features, and this information is then used as input for decision trees. So since the state-of-the-art method outperforms alternative baseline in explanation accuracy, we chose the GNN explainer as the subsymbolic method F. And as a method for extracting the rules, we use the standard machine learning mechanism decision trees. And then these decision trees can be linearized into decision rules. The classification by the decision tree is binary and based on whether the node is considered influential by the chosen subgraph, stemming from the edge mask, which is a 0, 1 valued vector, and therefore our target attribute for the white box model. And the attributes are extracted from node edge and graph meta information from the explanation subgraph. Since graph architecture offers more information than tabular data, it's vital to take graph-specific data, such as network motifs, into account. And in order to enhance the user-friendliness of our approach, the attributes are then personalized to the domain by mapping them to their respective domain terminology. The feature selection rules are generated analogously with the corresponding node feature mask. We used to try out our approach, we used the MUTAG dataset, which is comprised of molecule graphs labeled according to their mutagenic effect. And there we carried out graph classification with a vanilla graph convolutional network. And in the next step, we generated edge masks and node feature masks with the GNN explainer, and then applied the decision trees. So here you can see some first results. So these are model level explanations. So for example, in terms of features, in terms of molecules that are mutagen, our explanation would, for example, look like if molecule contains atom C and atom O, or for the edge rules, if atom has more than 2 bonds and if atom is part of an atom ring. So the exacted node rules gives the user a comprehensible idea of the network motifs that are influential in the GNN's decision making, either being part of a cycle motif, so for example, an atom ring, or with a high degree, so more than 2 bonds, or not being part of a cycle motif and having only 1 bond. Also, the node feature rules represent clear explanations which atoms, for example, atom H, are influential in their respective classification. So we can see that Subgreg correctly identifies that atom N and atom H are not being in the molecule is influential for classifying it as non-mutagen, which is the chemical group asanid, which is known to be mutagenic. No-node selection rules with a low Gini impurity could be extracted for the non-mutagen category. That's also interesting, as it indicates that no feature is influential enough to generate a model level explanation of when a molecule is classified as non-mutagen. And we report the sensitivity to show to which extent our explanation can function as a model level explanation. Sensitivity here indicating the ability of the decision tree to correctly classify a node or a feature as influential. Sensitivity lying here between 72 for mutagen node selection rules and 98 for mutagen feature selection rules, and therefore indicating a high level of model explainability.
And now you have 3 more minutes to go.
3 more minutes, okay. So, we have proposed this conceptual vision for how to approach generating more user-centric rule-based explanation from subsymbolic instance level explanation to improve model level understanding. And our initial experiments show that even with this very simple subgregs model method where we use decision trees, we do get some surprisingly effective results in terms of meaningfulness of the explanations, and with a high sensitivity, so high capability to explain, to have a model level explanation. In further research we're working on, though, we're using semantic web technologies, where we use inductive logic learning to allow for deeper integration with background knowledge through the use of domain ontologies, so that we have a much more structured background knowledge base, which to use as a resource, and also to create instance level explanations for the individual predictions. And also then being able to calculate the fidelity for our explanation from the student model, so the inductive logic learning, and towards the teacher model being the graph neural network. And furthermore, the advantage of then including semantic web technologies would be that it comes with reasoning capabilities. Yeah, that's all from my side. Here the references, and thanks for your attention.
Thank you so much. So we have time for one or short quick question. Anyone in the audience wants to ask a question?
I'd be maybe interested, because you're mentioning like Siemens on the slides. Did you use it in some domain-specific application already?
We haven't used it yet in a domain-specific. We're looking at one use case right now. We haven't implemented it yet. We are, but where we're trying to use it is in a cybersecurity use case.
Okay.
Yeah.
Thanks.
I have a quick one on the customization. So how can you customize? You can take any graph or any domain knowledge that you can customize the approach, and then how you do link concepts or informations.
Yeah, so what we're working on right now is the use of ontologies, and then integrating these ontologies with the graph neural network data beforehand. So you have that customized domain knowledge, and then you work with graph neural network embeddings, but then you want in your explanation, you want the explicit domain knowledge again, right? So that would be the customization part.
Okay, got it.
Yeah.
Thank you, Anna.
Okay, we would have now the invited talk of Zach, but it seems that there was a misunderstanding with the time differences. I'll just, maybe Arthur can say something about, because we don't know exactly.
Hi everyone, can you hear me? Yeah, I've been trying to contact Zachary Lipton, and yeah, without success right now. So yeah, I believe it may be some misunderstanding with the time difference. So he will probably be here in an hour, which is unfortunate. So what I can think of is I'll ask him to record a presentation that we'll try to add to the workshop program. Yeah, apologies about that, disappointing, but it was probably quite difficult to organize everything with the time difference. We had the Central European summertime and the yeah. Let me just see if there's any updates from Twitter and the emails. Yeah, I don't think they're checking their emails right now. So I'm not sure how we'd like to proceed, whether you would like to wrap it up here or have more of a discussion. And
Maybe we can well, give a chance to ask more questions to the speakers. Especially, I mean, Theodoros didn't get one, but maybe that's an opportunity for him to answer the questions. I know he did on the chat, but he can also do it to the audience, and we can probably have some more questions on the content.
Yeah, I think that's a good idea. Yeah, allowing people to maybe unmute and have a bit of a discussion. Yeah.
So maybe Theodoros, if you could, yeah.
Great. So let me repeat the question. If I have analyzed the compositionality of filters, and if we can group them for the sake of articulating complex concepts. So thank you very much for the question. We have analyzed the compositionality of filters by counting the number of unique filters and atoms used in explanations and how many times are reused in those rules. Regarding the second part of composing and grouping them to form more complex concepts, we didn't measure that in a quantitative manner. We only visualized the filters and how this can be grouped in a rule to form a complex concept, which is the explanations essentially. So we can say that a scene, for example, is composed of some subparts which are explained by each filter or each atom used in explanation.
Okay, thank you, Theodoros. Yeah, I've seen a question from Krisha to Anna, and so can you integrate the background knowledge with the GNN training? I know you did answer, but maybe you have more to say.
Yeah, not really. So we haven't done so in this approach because we just used a very simple method trying to validate our conceptual approach. But we are working right now on, like I've mentioned, on another method where we're trying to integrate the domain knowledge, which is in a knowledge graph, so in an ontology, with the information we feed into the graph neural network. So therefore trying to integrate that domain knowledge into the GNN.
Okay, thank you, Anna. Any other questions or comments? Feel free to chat it if you. Okay. So there's a question from Simon to Theodoros. How did you choose value for threshold for forming elite groups? Arbitrary or heuristics, clustering, anything else?
All right, yeah. Thank you for the question. That's a very good question. So in the paper, the value was chosen quite arbitrarily in that sense. So we chose the mean threshold activation across the set of images on the training set. So basically we forward pass the training images, record their activations, and then we choose the mean threshold, the mean activation as a threshold. We could also do that for a quantile of the activation, like the top 0.05 percentage. But we're also working on automating that stuff of choosing the threshold via an appropriate clustering or quantization technique that results in minimal information loss in the future. But in the paper, we have done that quite arbitrarily, choosing a mean threshold, for example.
Okay, thank you. We have a clarification from Krisha on Anna's work. So actually you meant, can the knowledge aid the training? So is it something you noticed during training, Anna?
Yeah, we don't really have very conclusive results on that yet. So can't answer that question yet. There might be an advantage. But it remains to be seen.
All right, okay. Thank you, Anna. Any other comment or question?
Okay, but Zach hasn't joined, so I guess we can close it here.
Yep. Sounds a good idea, Veronica.
Yeah, guys, thank you both, Veronica. Yeah, thank you both, Veronica and Freddie. I don't think Jack will be able to join, so I guess we can wrap up. And as I said, invitations were sent, but I suppose the time differences were misunderstood, and I'll seek to obtain maybe a recorded presentation. We did receive the title and everything, so I'm assuming that it will be disappointing for Zach as well to find out that he missed this, and he will be keen to give the presentation. So I'll try and put the recording and the slides and make that available in the web page.
Yeah, I recommend it. You can also check out his blog in the meantime. It's really funny. Thank you all for joining the session.
Thanks very much.
Thank you very much, guys.
Thank you, everyone.
Bye.
Bye.
Bye.